Hello, welcome to this live technical discussion series. And today we are going to talk about very important topic, which is lessons learned from sequential earthquakes in Turkey. And we'll be having Dr. Deniz with us shortly. He is a PhD in earthquake engineering and who is born, raised, educated in Turkey. And incidentally, he is streaming live from Turkey only. He was staying in Turkey for his education, etc. And even for this survey related to earthquake, he was there for last week, as I believe. And he's having specialization in field of structural dynamics, performance-based design, collapse prediction related to providing resilience for operational recovery after high seismic events. And he's working as an EIT in the structural department of Martin Incorporation. Okay, so very shortly he'll be joining with us. So before that, there is a small announcement that we have just launched a unique online course for design of steel structures as per AISC 36022, along with software applications, StatPro and RAM connection. So link for the course is mentioned on the screen. If you're interested, you can visit this link for more details. Okay, so let's get started now. Hello.
Hi, Bhavin.
Hi, hello, Dr. Deniz. How are you?
I'm doing good. How about yourself?
Yeah, I'm also doing good. Okay, so welcome to this live technical discussion series. And we are very much thankful of you for sparing your valuable time with us for discussion on this very, very important subject for the structural engineering field. Right. And after this devastating earthquake in Turkey, now there are so many questions, so many debates, are going on with respect to fundamentals of earthquake resistant design. So we would like to hear from you, from your experiences, your insight for this important subject.
Thank you, Bhavin. First of all, thank you for the introduction. I would like to add one more thing.
Yeah,
I completed my undergrad degree in Turkey, civil engineering, and then I pursued my master degree and PhD degree in the United States. And I was in Turkey. I'm still in Turkey, and I'm streaming from Turkey. Currently, I'm in Izmir Institute of Technology, and when we move on, I will demonstrate some information about our resonance team, the logistic, like where we have been, and then which places we visited. We will come to that point. Before that, I would like to mention that I would like to mention our presentation overview. So we will have some important notes before we started. And then I will mention briefly about the background. This will include lots of things: seismic, earthquake, performance-based design, elastic design. I thought that this will be good for our attendees. And then after that, I will jump to observations. These will be discussions with the research studies, and then what I observed in the field with our resonance team. And then after all, we can get the questions from our attendees.
Yes. So overall, can we say around 45 minutes of talk will be there from your side, and then
yes.
Last 15 minutes we can spare for question and answer, right?
Mm-hmm. And but of course, before I start my presentation, I would like to mention that this was a disaster, and please do not forget about this disaster. And I'm sorry for all countries affected from the earthquakes. Today, we mainly focus on Turkey because our resonance team was in Turkey. and we did our observations in Turkey. But the other country is also affected from this earthquake, and I'm sorry for all of the countries affected from the earthquakes. And let's jump to important notes. I would like to mention that the science behind earthquakes are ocean. It's not just like one professional area. So there are seismologists, geotechnical engineer, and structural engineer. So today we will focus on the structural engineering part. So that's why we will discuss seismic design philosophies against seismic events. I can answer your questions maybe briefly on like seismology or geotechnical stuff, but I highly recommend to ask question on the superstructure above the ground. And that was the first important note. And then the second one, we will discuss some collapses and then the damaged buildings here. But please and please do not forget that this is preliminary analysis. What I mean with the preliminary analysis, these are based on observations that it might be based on images and videos and the pictures, or it might be based on what we observed in the field. But it's not the concrete outcome or concrete result or like the concrete fact. So these comments here might not be like the considered as a final conclusion. So that's why I put here the schema. So the final conclusion about like what was wrong, what happened there, and then that will be provided based after the detailed analysis. So again, today we will just talk about preliminary analysis. You can think about it's like initial thoughts. So then let's start with the background. So our reconnaissance team was we stayed in Adana. You can see Adana here. And then we traveled every day to the affected regions in Turkey. And then we mainly, we visited like around 6 cities, not all of them, but tried to visit the most damaged ones. And so brief information about what happened there in the region. So 2 earthquakes over magnitude 7.5. So this is huge. And then thousands of aftershocks. You can see the green dots like those are, and if you zoom in that data, you can find like more and more like aftershocks. And the total death toll is over 50,000. And over 20,000 buildings collapsed, but with the damaged and then the demolished ones, the number will be probably over maybe 200,000. So it's a big disaster there. And then our reconnaissance team from United States and Taiwan, we were there, people of 5. We investigated many of those cities, and I can say that maybe like for the Antakya, this region, maybe 80-90% of the city was destroyed. So this is really big devastation here. And then when we talk about our observations, please also note that so we cannot generalize those collapses based on the every city. So every city has different condition. There are like a loose soil ones. You can see like a liquefaction collapses, and that's why like we cannot provide even in the preliminary analysis, we cannot say all over this happened in all over cities in the 10 cities. Just the beginning note. And then I would like to show the when I say like 2 earthquakes over magnitude 7.5. So these magnitudes, we don't use it when we design structures. We don't say, okay, let's design this structure for magnitude 8, magnitude 7, or magnitude 6. So we don't use this term. This term is just to explain the energy releases. So you can make a analogy in between the magnitude and the energy released. So you can see like it was like one of them was around like 7.7, 7.8. You can see the energy released from that earthquake. And you can see like 6.1, 6.2 is equals to Hiroshima atomic bomb. So we are talking about huge energy released here, like huge energy. But again, we don't design buildings based on magnitude 7, magnitude 5, or any magnitude. This is just a term to explain how much energy released from the earthquake. And again, there is not just one parameter to explain this magnitude. There are other parameters as well, or like research studies, or like the explanation for that. Anyways, so when earthquake happens, there are lots of stations to record the data, the ground motion data. We call this ground motion data. And this is a typical ground motion data. You can see the acceleration, the time. So this is from one station, and this indicates only one direction. So earthquake doesn't happen only horizontally. There is also vertical component. It's not unidirectional. And so you can see here it says 0.3 G. In Turkey, the PGA, we call it PGA, peak ground acceleration, was around 0.7 G. So which is pretty high, but also we don't check just PGA, just acceleration. There are also other parameters: acceleration, velocity, and then the deflection. Displacement. So when you check PGV, peak ground velocity, it's really high peak ground velocity we obtain some of the regions. So this is really important earthquake based on high PGV, and I can say that maybe like high vertical acceleration too. So we got this data from one station, and then we transform this data to like a pseudo acceleration response spectrum. Why we transfer this ground motion data to response spectrum? Because this shows us the response of the single degree of freedom system. So based on this, we can talk about the acceleration we will obtain in the building, so that we can calculate the inertial forces. But this is from one station, data from one station to one response spectra. But how we determine so we don't use, when we design structure in the linear design, of course, when we use the code, when we do the linear design, there are other designs too. You can perform like a real-time history analysis and stuff. But when we use the linear design, we use design spectrum. You can see the black solid line here. That's what we use. And how we get that solid line is based on all the earthquakes happen in the region. We determine that. But this design spectrum is not just parameter of one thing. There are like many parameters involved in it. For example, one of the other big parameters is like the soil. So the soil condition, when soil condition change, this design spectrum also changing bigly. So that's why in the code, ASCE or Turkish code, like 2018 Turkish Seismic code, you can find different design spectrum for the similar region based on the soil class. And then once you have this black solid line, so basically this is based on the data, and then in the seismic codes, ASCE or the Turkish code, you just get this black solid line, you see that, and then based on your period of your building, you pick the design acceleration. And then this was the seismology part, and then the ground motion part. But now we will talk about like when we get this design acceleration, how we use design acceleration, how we design, or like what are the options like for the seismic design philosophies, like what options we can go. So basically, I kind of categorize here like into two options. You can see like elastic design and performance-based design. When we say elastic design, so elastic design, when we say elastic design, it's the linear design, and then all the components, structural components, still in the elastic behavior. And then mostly we see elastic design in the dams, for example. But when we go to residential buildings, we prefer performance-based design. What is the big difference between them? The main difference in between them is the one of them is like, of course, the main difference is the cost, right? So when I say cost, don't think that like we don't spend money to save lives, or we don't sacrifice money for it. So it's different issue. We are talking about huge money here, and when we talk about performance-based design, again, people are still safe. We will talk about it. What is the design philosophy? I will explain it with the analogy as well. But the main difference in between is the cost, also the return time. So most of the time, like when we design the buildings, residential buildings, the return period is 50 years. So we give the lifetime for the buildings like 50 years. And when we design buildings in the elastic, it's much longer. So in order to understand performance-based design, we need to understand what is the brittle and ductile terms. So we have different construction materials, for example, concrete and steel, right? So concrete is brittle element, and then the steel element is the ductile. So there is a big difference in between them. The difference between them is the significant plastic deformation. So ductile elements can exhibit significant plastic deformation. But when we check the brittle elements, concrete, their plastic deformation is very low. So we split it here. It might be hard to understand for some other people. So when we say elastic and plastic, so let me show you like a quick demonstration here, so you can see this, right? So now I will apply like some loads on it. You can see like I'm now like pulling it, right? Pulling it, and then when I release my load, it goes back to its original shape, right? So this is called elastic design. But what if I increase the loads that I applied? So if I keep increasing the load, you can see, and then when I release my finger, it didn't go to original shape back. So the difference is called plastic deformation. So when any material goes to plastic deformation, it dissipates energy. So you can see here the green line. The green line is the green area here is the energy dissipated by the ductile element. So we call it is the energy dissipated area, or you can say toughness. But if we check one brittle element, again, if we zoom in the camera here, so you can see this, right? This is like a brittle element. And if I apply force, you can see like it's deforming. And then when I apply a little bit more, it just break. So it's plastic deformation capacity. Again, you can see here, like when I apply a little bit load on it, it goes and then come back, right? But if I apply more load beyond its elastic level capacity, so it just break easily. So you cannot see that plastic deformation here. That's the difference between concrete and then the rebar. So that's why for the performance-based design, we highly prefer ductile materials. That's why we use reinforced concrete instead of concrete material itself. We provide rebar inside concrete. That's the idea between brittle and ductile. And then when we design buildings, the performance-based design that we said, so if we use like a ductile elements, and then if we exhibit ductile behavior, instead of designing the force level here, elastic structure, so we can decrease it to like a minimum design force. You can see here, we can design the buildings at this level.
Yeah. Small interruption. We are not able to see your cursor. I think you might have to move into the other screen.
Okay. Yeah. Sorry.
Yeah. Now we can see it. Right.
Okay. So you can see here the maximum force for the elastic design, right? once we go back to once we use the performance-based design, we can reduce this load from here to here. There is a huge difference, huge reduction here. But of course, this comes with some other disadvantages. We will talk about it. But using ductile elements provides us to provide this reduction. So basically, when we talk about performance-based design, again, so this let's talk about the lateral seismic force here. You can see this is the force that we consider elastically, and then with the R value, this R value is parameter of lots of things. Is it like a moment resting frame or shear wall system, or like a concrete building, steel building, timber, masonry, whatever you use? There are lots of parameters to determine this R, but basically based on the R value, based on your system, you pick your R value and decrease the elastic load to the design load. Here you can see. So we design the buildings basically with the reduced earthquake loads. But of course, when you do that, the return time, when I say return time, the lifetime of the building decreases to 50 years too. And then when you see here, there are some points. We can say that, like, again, fully elastic. It says fully elastic right here. So it means that if we obtain the base shear is the earthquake forces we obtain at the base. If you obtain the force level here, this building still will stay elastically. But when we keep increase when we get the earthquake load more than the design, so what will happen is we will see the damages on the building. But of course, when we say performance-based design, we don't design the buildings to collapse, right? So we design the buildings at the performance point. The worst case, it will go back to the collapse prevention. So the idea for the performance-based design here is surviving the main shock, surviving the main shock happen, and then leave the building suddenly, like quickly leave the building. So the whole point here, if the earthquake happens, we are talking about not like the small earthquakes, of course, something like this, like a high magnitude, something like the earthquake that caused the higher acceleration from the design level. So then the building can go to like you can see here, the building can go to like a damage here. But again, still they shouldn't collapse. They should stand, like they should damaged, but they should stand after the first main shock. And then the idea again, survive the first main shock and then leave the building. So this might be seem to like complicated to everyone, because now you can think that why we design buildings to, like a damaged, why don't we design them like to elastically? They might just stay like this. If you design them, like in the elastic region, so they will stay fully elastic, like the dams that we see. But again, the problem with that is the cost. I will explain that with an analogy after I show, like after I demonstrate here the building components. So let's quickly check the building components. Like when we say like what is the life safety or immediate occupancy, what are those levels and what kind of elements damaged, like that. And then I will show one more analogy to explain in a better way what is performance-based design. So you can see here, this is like this is what people see from the outside. This is what structural engineers see: the components, vertical structural system, lateral force resisting system, or diaphragm, and then the collector elements. And then let's look more into the components. So we have diaphragms at every level, and we design them to remain elastic in the performance-based design. And then we have gravity system, the columns. We design them to remain elastic after the high seismic event. We are talking about high seismic event here. We are not talking about like low seismic events. And then we have collector elements. You can see here, we also designed them to remain elastic. However, you can see the lateral force resisting system here. That might be shear wall, we will talk about it, or that might be moment resting frame. But we designed them for significant inelastic deformation. Inelastic also similar thing with the plastic. So significant plastic deformation to observe the earthquake energy. But when I say observe earthquake energy, not on the ground, observe the earthquake energy on the building. Of course, like after large earthquake, the building will often have to be replaced because of the damage. And here, again, the goal is life safety. And these are the common lateral force resistance system. We have moment resting frames. You can see here, we have brace systems and we have shear walls. And you can see like the plastic hinges or like the damage yielded brace or like the cracks and the yielding in the reinforcing steel on the shear walls. Now, so I kind of explained a lot, I know, but I have better analogy to explain performance-based design because you can understand in the cost way better, I guess. So when we design the cars, right, you can get like you can design them elastically, like tank here, you can see, right? Or you can go to performance-based design. What I mean is like a normal car, right? So when you buy a car, anybody, when you buy a car or when people sell a car, because you can do like an accident one day, that's a possibility to make an accident, right? People can crash. People, it might be like some collision impact energy can go to inside the car. But just because of that, we don't drive tanks around on the streets, right? So that's the one analogy that you can understand the cost difference in between elastic design and the performance-based design. And to understand the damage, so if we think about like the car here, so this is like how they designed the car. And then if we think about the car design, so you can think that the accident, the collision is the high seismic event, not like the low ones. Again, high seismic event. So we can make this analogy like the accident, collision, or the crashing is the high seismic event. So when the crashing happens, as you can see here, there are like a crashable zones, and then the safety zones. And when the building crashed, as you can see, the crashable zone is sacrificed. Why it is sacrificed? To dissipate the energy, the collision impact energy coming to car. So somehow you should dissipate that energy. So as you can see, they use like a different level of steel. When you use ultra high strength steel, this is more brittle than the very high strength steel or high strength steel. And then when you use like high strength steel in here, when you use the like high strength steel here, you can dissipate the earthquake energy, the collision energy, while you can see the safety zone where the people are, it's still standing and safe. So basically you sacrifice one part to protect the other side. This is the similar idea with the performance-based design. But also you can think that like if you go like elastic design again, think about Tesla's Cybertruck. Why its shape is like not like a good like the sport cars, because it's not easy to process the ultra high strength steel also. So you cannot come up with like a sport car using the ultra high strength steel, today's technology. It's not easy to bend it and then check the cost also. So that's the idea in between elastic design and performance-based design. And then when we design the building or when we design the car, in this example, you can see we have car A in here and car B, right? So when you check the car A, it's like a driver is still alive, right? And then when you check the car B, driver is still alive too. But what is the difference in between these two? is one of them is elastic design, one of them is performance-based design. The only difference is in between two is this car need to be repaired, or you need to buy a new car. So you need to update your car. But the people are safe. Again, so performance-based design, the main goal is the life safety. So we sacrifice some of the structural components, or in the car design, they sacrifice the one part to save to dissipate the earthquake energy, and then they save the zone. And then you can come up with like a lot cheaper. We are talking about maybe 10 times cheaper structures here. So again, think about it. Do you wanna drive a tank because because there is a possibility that you can make an accident one day? So that's why like we design buildings in also elastically. Sorry, in performance-based design, we don't design them elastically. But of course, why we design them elastically? Because there is an importancy factor. So that's another discussion. And then I would like to mention briefly here that we mentioned the performance-based design. We mentioned sacrificing some of the structural components, right? But when this happens, what are we gonna do? Are we gonna demolish this, like let's say the building damaged in the life safety level or the collapse prevention level, and then there are like a severe damages on the building, columns in the girders. So are you gonna demolish the building and then rebuild it, or the question is like, can we come up with an idea to repair it, like the cars? When you crash your car, right? You can go to like a repair shop and you can get it repaired maybe. So can we use the similar idea? Yes, that's why there are some passive energy dissipation devices. By using those devices, you can localize the damage, and then you can basically repair those devices after the earthquake. This is not just one idea. There are other stuff too, like probably most of you know, like a seismic isolation technology, but this is not for the similar working mechanism. This is to dissipate the earthquake energy. This is reduced to earthquake energy, and there are other stuff too, like for example, mass temper. This is used in Type A 101. So again, there are others. There are other seismic devices to provide better solution and economical solutions to buildings design. But here the question is like, you wanna get a design with the low fee in the first place, or low fee when the earthquake happened. So basically, let's say you have those passive dissipation devices. After the earthquake, you don't need to demolish the building. This is the second cost after the earthquake, not the first cost. First cost is buying these devices will be, of course, more costly. But when you have those after the earthquake, the damage will be, the cost will be a lot cheaper. Instead of demolishing the building, you can just repair it. Like you can think here, instead of buying a new car, you can just repair this car. Of course, if the engine is safe. And then, so this was the brief background about like what is elastic design, what was the magnitude, how we comment, how we got the ground motion data, how we got the design spectrum, and if you have questions, of course, we can dig into more to those. Now let's check the observations that we got in the field. So the mostly what I saw, what we investigate, what we observed is the buildings are mainly there are like reinforced concrete buildings with infill masonry, and then when you walk around any cities, you can basically see the cracks, those kind of cracks you can see here. So you can see those cracks, diagonal cracks in two-way. Most of the buildings. So the question is why we have those cracks, right? Why we got those cracks? Because when not we one structural engineers design these systems, as you can see here, we have the frame. Let's say this is like a column, and we have like a columns and the beams here. When they design this building, they don't provide any gap. So if there is no gap, so think about this partition walls here, its demand, its capacity versus the columns here. So when earthquake happens, these columns get drifts, right? But they designed to, to resist some drifts. But how about those partition walls? When they get those drifts, as directly they start cracking because their capacity is not enough for that. They don't have sufficient capacity to exhibit some drifts. So this is the explanation, and what I see at the field, you can see this is one of the building. Again, I'm trying to provide like a little examples from every discussion, but we will provide like a detailed information in our report. So you can see here like we have one building. On the left is the building. It's damaged. You can clearly see with your eyes, right? And then when you check the right side here, you can see those diagonals here, right? The diagonals you can see clearly here. So that's from the region affected in the earthquake. And then the other issue that I realized is the captive short columns. This is also one of the big discussion that it's been like decades. So when you have openings and then infill walls, these openings, you can think that this might be like window, right? And then when you have like a window in one side, or like you can see here, there is window, right? And then the bottom part is like infill wall. So the openings is kind of might be window or like a door or anything that provide openings there. And then we have again reinforced concrete frame, you can see, right? So most of the time you can see those cracks where the region we have like openings, but also you can see like a cut, like direct shear for like shear failure. So when I was in the field, this is one of the example. You can see the full building here, and then on the right side, right picture, you can see like we have windows here, right? So we have openings. These are the openings, and then the bottom part is like a continuous like a infill partition walls, right? And then because of that, so this provide here like a short column effect, and then because of the shear forces, and then you can see the cutoff here clearly. So this is one of the other issue. And then the other one, plastic hinges. So plastic hinge, when we say plastic hinge, so this is actually what we want to see instead of collapses, instead of like shear failures like that, or instead of like those. What we want to see is the plastic hinges. Why we want to see plastic hinges? Because when you see plastic hinge, it means that in the hinge part, this element, the structural element, goes to plastic deformation. So plastic hinge, you can make a connection, plastic hinge with the plastic deformation. So when we have plastic deformation, what we got is huge energy dissipation, right? So that's why like that's basically what we designed the building for, performance-based design, right? To getting those plastic hinges. So, but we got those plastic hinges like the car crashing, right, after high seismic event, to see the dissipated energy, right, to dissipate the earthquake energy in the building. So as you can see, but of course, so how we want to see those plastic hinges? We don't want to see them randomly, right? We want to locate them. So as you can see in the here, the top left part of the picture. So we want to see those plastic hinges, the mainly in the, you can see the number 1 here, right? And then number 2 here. And then, so this is kind of providing, this is called also like a sway mechanism. There are other ways to get those plastic hinges as well, but this one is called like sway mechanism. And then if it's getting more and more and more, of course, one point it will collapse. So this is the basically collapse mechanism or survive mechanism, but we don't want it to collapse. What we want to see is the when earthquake happen, the main shock, right? So we want this building to stand with those plastic hinges by dissipating the earthquake energy, and after that, the building should be left. Anyways, let's see the observations that we got in the field. So you can see the building on the left. So what we got is here like a plastic hinge in the beams, in the girders here. So that's what we kind of want, because we don't want the plastic hinges come up like in the column in the first hand, right? So this is kind of, and then as you can see, the building is still standing after 2. I say you can argue with this, but I say 2 main shock with the 7, 8, 7, and 7.5. Sorry, yeah, my cursor. So you can see the building here. Yeah, so after 2 main shock and lots of aftershock, like thousands of aftershock, it's still standing, and you can see the plastic hinge here. So this is when you see this building, lots of cracks here, right? And then those like a damage here. But this is kind of good design, because this building designed for this. And then if we check other plastic hinges, for example, this one, when we check this one, this is like again mid-rise building, but when we investigate this building, we obtain those like damages, not on the beams, right on the columns. So this is like this is a thing we don't want it compared to other one. Of course, you can see those like plastic hinges not on the buildings. You can see them on also bridges. So this is one bridge example in the region again. If you focus on the base of those piers here, right, you can see the plastic hinges. And when the people design bridges, they want to see those plastic hinges at the base of those piers. But when you also like investigate like some other buildings, for example this one, you can see the plastic hinge is not in the base, it's in the middle. So this is kind of big question mark. But to answer this question, so it's not easy to answer this question. It's interestingly the hinge in the middle. The question is like why. To answer that question, you need to like a more detailed drawings and stuff, like what are the longitudinal rebars at this position, like at the middle and at the base. So we need to see all of those. And then the one other thing that we obtain, liquefaction, basically, but this is we saw lots of examples of it. Now the figures might seem like a kind of complex, but how you can understand, or like what is basically liquefied soil. So we have 2 options, like not 2 but like lots of, but we can say like one stable soil, right? You can see here stable soil, and then one is the liquefied soil. So what is the difference in between them? So this one is stable, but however this one, briefly, we can say that the soil flows like a liquid. So that's the difference. So that's why you can see like settlements and this kind of damages. And when we check the area, you can see the like the settlement here, like and this is like Robert Dowell from California State University, and then you can see the settlement. It's huge. And then there are buildings, like lots of buildings close to not close to in this region. So what can this do? It can cause like a settlement like this. But when I say settlement, don't think like the Pisa Tower in Italy, right? That's a slow settlement. This we are talking about the compared to that, like immediate settlement. But the building is just slowly like a falling down. When we investigated this building from other sides too, like the pictures and everything we have, it has like a low impact on the building that it's standing. So that's why it was like easily, not easily, but it might be kind of initially again preliminary commented that it's just settlement issue. And then we also obtained one building, split it into two parts. You can see here why we got this, because the other two side of the building, this side and then the other side is just like a settled, but however this region was standing. So that's why the building is split it into two parts. So we also obtained like liquefaction issues there. And then the one other issue is the soft story. This is also one of the common failures that we saw. So soft story might occur because of the soft story mainly we saw in the first floors. Why we see that? Because of when structural engineer provides, or like the designer, or how they go through this building, they provide large openings in the first floor, and then those large openings you cannot provide like those infill masonries and stuff. But however, in the top portion you have those things, so that's why you created like a weakness here. So, and then during the earthquake you basically see the collapse in the first floor. And if we check the example for that, this is one of the example you can see clearly. You can see the cars here. So there was another floor here, but after the earthquake, it just suddenly collapsed to the ground. And then you can see the cars. And in the region, probably I saw lots of shopping stuff, like maybe like shopping places provided in the first floor. So to provide those shoppings or the garage openings, the designers or like the engineers, they provide like large openings in the base. So that's caused those like a soft story failures. And then when we were investigating, we realized that like how you can understand one building is designed before like a 2000 and or like after 2000, right? Because the seismic code in every country, year by year, time by time, it's evaluating, right? Like it's not constantly. Like 50 years ago, people were using different seismic codes, seismic provisions, and now different. So that's why one building might be designed with the old provision, and then the new one probably designed with the latest provision, right? So when we check the buildings, you can see those rebars. And when we talk with the local people, they say that those rebars used before 2005. So what is different? What is the difference between these two bars here? One of them is so smooth, you can see, and then the other one has some roughness on the surface. So this roughness provides better bonding with the concrete. But before, structural engineers were using like smooth rebars. So that's the difference. So when we see like the rebars like that in the field, we understand this building is definitely designed or built before 2005. And when we check the code, evaluation of the Turkish seismic code, you can see this one until 2000, and then the other ones come like 2007 and 2018. A 2018 one, the code provision, I guess, is well defined, and again, it's not perfect. None of them is perfect. Every time they are open to more, improvement. They should be evaluated and developed more. Um, More studies should be conducted. But if you design the building, if the structural engineers design the building using the latest code, vice versa, the code from 1950s, that will be a huge difference, right? So that's why, again, and if we go back to our performance-based design discussion, that when we design those buildings with the performance-based design idea, um, there is a lifetime for that, right? You shouldn't forget. And one of the main observation I can say that seismic retrofitting is really important. How can I understand that? Because one of the region we visited, all the schools seismically retrofitted like 2 years ago, and none of them even you cannot see moderate damage on them. So seismic retrofitting is really important in the world, not just in Turkey. Lots of places, like for example California, San Francisco region, right? And then so there are also buildings, new buildings, you can say perfectly designed, but how about the old ones? They design with the old provisions. So those ones should definitely be retrofitted. So that should be, I guess. Of course, there is a cost issue with that, but um, this earthquake in Turkey, I guess, in this region, let's say, definitely show that the seismic retrofitting is really important for the old buildings. You can think also like engineering service. Uh, so that's one of the things that I would like to mention. And then I think I completed my part. I would like to say thank you for listening to everyone. Now I'm ready for your questions.
Yes. Okay. So thank you for sharing preliminary thoughts on this study, and definitely we'll be having more interesting discussion on this. So meanwhile, we have started receiving few questions from the participants. Let's take few of them. Okay, a lot of buildings collapsed due to joint failure and not member failure. So which kind of strategy we might have to change?
So that's a yeah. So when we check those collapses again, if you go back here, the first important note. Let's open that one.
Yeah.
Uh, um, so if you go back here again, what we discuss here, preliminary analysis, right? We obtain some stuff, we observe stuff there, we check the everything based on with our eyes. But again, to change something or to move on something, right? So what we should do is we should get the detail analysis, like we should finalize it, uh, we should to give the final answer, the concrete answer. We need the detailed analysis. I agree. I also saw I also observed lots of joint failure, but again, I demonstrated lots of pictures, and there are more and more. We are talking about over 20,000 building collapsed, right? And then the total the number for the demolition will be maybe over 200,000. So there are lots of failure, lots of collapses, and lots of damaged buildings. So we cannot say it's joint failure only or member failure only. So there are again. So what about this building? So is it joint failure or like a member failure? This one, you can see even those glasses still standing. No even break on the glasses, right? So so that's why um, I cannot say it was joint failure only or member failure only. Nobody can say that at the point, right? we need the detailed analysis. But as a preliminary or initial thought based on that, we can say that like there are little bit of everything. That's my initial thought. I hope he's satisfied with the answer. And then this is the other question. I can't hear you, Bhavin.
Yeah, this is interesting question. What about design with two big earthquakes?
This is a great question. Thank you, Emreketen. I think he meant that sequential of
Yes.
earthquakes.
Mhm.
So here, when you check the any seismic code in the world, there is no like designing, I guess, the sequential of the earthquakes. And when we go back to our performance-based design table here, right? So when we design those buildings based on performance-based design, right? So we design the performance point is here, but they can go to life safety. The more likely maybe the collapse prevention at the design level earthquake. We are talking about again high seismic design level earthquakes. And then when this happened, the question is here, when this happened, this is the first main shock, right? So this happened, and then the building is damaged. So here, the one of the most important thing anywhere in the world, people should leave those buildings and they shouldn't go back, because damaged buildings might even collapse. Well, we also obtained like recently magnitude 6.4 happened, that also collapsed like not 7.5, 6.4 even destroyed like or like caused the collapses in the some of the weakened softened buildings. So that's why again, if the building design with the using performance based design philosophy, what should be the survive the first main shock and then leave the building. But the question that he asked, like two big earthquakes, that's a big study. So there are some other problems there, because what is the problem there is like that might be good research study also. Um, those ductile elements like rebars, those have like a finite strain capacity. So that's why it's highly more likely that we can obtain fracture due to low cycle. So this might be like a interesting research study. I hope he's satisfied with the answer.
Yes. Okay, next question is for the short column. That whether it has to be designed with over strength factor or special detailing, such as providing confinement throughout the length, is enough.
Yeah, good question. To answer this question, so I cannot say like they should be designed like that, or like they should follow any instruction here or there, but what I recommend, I can just tell my recommendation. The gap between those frames might be provided. So if the gap provided, so what will happen is, so you will basically you will not create this captive column effect. But again, if you don't want to provide gap, so I don't think there is one solution here. But if you don't want to provide gap, um, then not to overstrain, but definitely special detailing to provide like those like a shear case there, and then to provide like to protect the columns from this effect.
Yes. Okay, so thanks for the excellent presentation, Dr. Deniz. And as engineers, I think we should use these three parameters more wisely: cost, design, and construction. Okay, next point is why third mode torsion is important for seismic design.
Right, good question. But so in here, like that's other like this is a long discussion, because we don't have also like example and explanation on this one. But why it is important?
Right.
So basically, the torsion causes like extra forces on the two side of the building, and some of the like the buildings when we design them, some of them is like very strong, like for example shear walls. We have the strong in plane direction and then the weak out of plane direction, so it's kind of causing big problem there. But this is very brief explanation, like this is again long discussion.
Yeah. Okay, so a lot of buildings were failed. Was they or were they designed based on old Turkish code?
That's a good question. Again, and I think that um, I can again. My answer will be the preliminary one. Again, based on what we see, based on the rebars that we see, like the smooth ones, and that the one that I explained. I think my answer is like a yes. Most of the building collapsed. They were designed based on old Turkish code. But again, when they built, there wasn't a new code, right? So that was the code when at the moment at the time.
Yes. Whether any PGA at any particular location exceeded than prescribed in codes or zones classification.
That's a great question. So he mean the PGA. So again, but the point is here we are not designed with the PGA, right? What we use the design spectrum, and then what we get the what we compare the design spectrum is the response spectrum that we got from the recorded data in the stations. So we compare that. There is a little bit difference in between PGA and the response spectrum, and then my answer is in one region is the design was like I think they obtained like almost double.
Okay, one more question. Which type of failure absorbed maximum out of following? Soft story, liquefaction, lack of ductility.
Oh, uh, that's a great question. Um, well, all of them, all of them. Uh, lack of ductility. Lack of ductility is also like kind of one of the big issue. He means the not sufficient or like enough rebar in the concrete so that they can just fail like a brittle failure. Liquefaction again, there is no, as I said, there are 10 cities. Those cities are not for like a 10,000, 20,000 people. Many of them over 500,000 people, like a big cities, 10 of them, and we obtain like a lots of different failures.
From snaps from site, we could observe that amongst a group of structures which were identical, so some buildings were standing, but some building collapsed. So what could be wrong in the failed ones? Any preliminary thoughts on this?
Oh, that's a good question. But again, so for example, same design for all those buildings, right? How can we say that? Like, do we have the drawings from the buildings? I don't have drawings, right? So I need to get the drawings. Once we get the drawings from the buildings, then you need to get like a specimens and you need to test them, right? You need to get the concrete strength if the concrete strength is matching, right?
Mhm.
The rebar number is matching. So those, after we answer those questions, then we can talk about this.
Right. What is the performance and behavior of old load-bearing wall constructed buildings in this earthquake?
That's a great question. So we visited like several mosques, churches, synagogues. Those are like old masonry, old constructed structures, and then there are like a churches like a 700 years old, and they also like damaged. So again, the earthquake was really terrifying. It's a big earthquake. uh, Two big of them happened, like in 9 hours difference. Lots of aftershocks. So that's why like even, yeah, like those ones, again, those old load bearings, those are also like most of them brittle. They don't have reinforcement inside. Their performance was kind of questionable, but of course they are not like 10 stories, right? So when we talk about church, it's like not like 10-story building, mid-rise building. But again, we obtained some of churches, synagogues, and mosques also like damaged, collapsed.
Right. Okay, still questions are coming up, but we have reached to the 1 hour slot. So can we take a couple of questions, or we may organize, one more session whenever it is convenient to you, when you have, more detailed study done
Mhm.
on the subject.
Thank you so much to everyone.
Yeah.
Uh,
Excellent.
I hope
Yeah.
it was insightful for people.
Yes, it was an excellent presentation, and we will be looking forward for, more detailed discussion on this once that report is prepared, in detail based on the observations which are made on the site.
Okay. Thank you so
Okay.
much.
Yeah. So thanks a lot for sparing your valuable time. So with this, now we are closing this session. Okay, and we'll be meeting soon again on a very interesting live discussion. Okay. Yeah. So goodbye. So we are closing this session now.